Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL January 2024 paper of Chemistry Unit 1. On to question 1. We are given the first ionization energies of 4 successive elements in the periodic table. So if we go from P to Q, the first ionization energy increases. Then if we go from Q to R, there's a significant decrease, and there's a small rise from R to S. So P must be a group 7 element, Q must be a group 8 element, and R should be from the next period, and it's group 1, and S is group 2. So now in part A, we are asked which element has a full shell of electrons, full outer shell. Q would be the answer. In part B, they are asking which element could be in a gaseous covalent compound with the formula HX. So this is hydrogen halides. Hydrogen halides are formed with group 7 elements. So P would be the answer. In question C, they are asking what could be element Y in an ionic compound with formula YF2. So Y must have a charge of plus 2 plus. So Y must be period 2, so S. And now they want which element has atoms with the largest atomic radius. Since R and S are in the next period, they'll be larger than P and Q. Also, we know that along the period, so if this is our periodic table over here, if we go along the period, the atomic radius decreases. So S will have a smaller radius than R. So the largest atomic radius would be element R. Now on to question 2. We need the diagram which represents the electronic structure for nitrogen. Nitrogen has 7 electrons. So if we follow the Aufbau principle, so we'll have this. We don't need to go that far. So we'll have 1s2, 2s2. So we have 4 and we have 3 more left. So we'll have 2p3. Now in terms of orbitals, we'll have this 1s, this is 2s, and this is 2p. So this is 1s, 2s, and 2p. Now we know that there will be 3 electrons in the 2p subshell. So this has 1, 2, 3, 4. This is out. This has 4 as well. So this is out as well. So we are left with these 2 options. We have to remember that the electrons feel the subshells like this. So if it's a p subshell, the electrons will first fill the empty orbitals, and then if there are more, then they'll start filling the half-filled orbitals. So the empty orbitals will be filled at first. You won't have a case where electron will skip this orbital and go join here. So this wouldn't be the case. So C would be the answer. Now we need which species does not contain a total of 16 electrons. If we count, we have 12 C2. So 12 C2. So carbon has 6 and hydrogen is 1 over here. So number of neutrons would be 12 minus 6. This is for carbon. There are 2 carbons here, so we multiply 2 here, plus we will not have any electrons for hydrogen, so we'll have 6 into 2, 12. So this would be the answer. If we want to look into the other ones, this is 16,8 oxygen. So oxygen has a atomic number of 8 and a mass number of 16. So 16 minus 8. There are 2 oxygen over here, so we multiply it with 2. This is 8 into 2, so 16. For silicon, the atomic number is 14, so the number of neutrons is 30 minus 14, which is 16. For an ion of sulfur, for the ion we are gaining 2 electrons, but the number of protons and neutrons stay the same, so we don't have to worry about that. Sulfur has a mass number of 16, so number of electrons will be 32 minus 16, which is 16. Now on to question 4. We are given that each of the pair of values are the atomic numbers of elements. We have to find which pair of atomic numbers are those of elements that are in different blocks. So the periodic table has 3 blocks. So the first 2 groups are S block. So group 1 and group 2. This is the S block. This over here, so group 3 to 8, these are the P block elements. They're called S block elements because the highest energy electron goes to fill an S subshell, and this is called a P block element because the highest energy electron goes to fill a P subshell. In between we have a D block, which you will not need in S. Now for electron number of 5, we'll have a configuration of 1s2, 2s2, 2p1. So this is a P block element. For 9 we'll have 1s2, 2s2, 2p5. So both of them are P block elements, so this is not our answer. For the next one we have 1s2, 2s2, 2p6. So this is a P block element, and for 16 we have 1s2, 2s2, 2p6, 3s2, 3p4. Yeah, both of them are also P block elements, so this pair is not our answer as well. For 13 and 18, let me erase the previous ones. For 13 and 18 we have 1s2, 2s2, 2p6, 3s2, 3p1. For 18 we have 1s2, 2s2, 2p6, 3s2, 3p6. So both of them are P block elements, so they are not our answers as well. Now for 16 and 20 we have 1s2, 2s2, 2p6, 3s2, 3p4, and we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So this is our answer. We don't need to calculate the electronic configuration over here. We can just look at these values over here. So let me write the values down: 5, 9, 10, 16, 13, 18, 16, 20. Now compare this with the periodic table you'll have at the bottom, the last page. So if we come over here, we see that 5 and 9 are both p block elements. If I divide the periodic table, these two are the S block elements, so this is S block, and this whole thing over here is the P block. Now 5 and 9 are both in P block, so they are out. 10 is over here, 16 is over here, both of them are in the P block, they are out as well. 13 is over here, 18 is over here, both of them are P block, so they are out as well. 16 is over here in the P block, while 20 is out here in the S block, so they are in different blocks. So 16, 20 is the answer. This is the way you do it in your exams. In question 5, we are asked which molecule is polar. Now carbon dioxide has a linear shape, so their dipole moments cancel out, so this is not our answer. Same case over here in CCl4, this is a tetrahedral shape. The dipole moments are all equal, so this is L plus. The dipole moments are will all cancel out, so you'll have this. And the dipole moments will cancel out to become 0, so this will not be polar as well. BeCl2 is also non-polar because it has a linear shape. Now for NH3, NH3 has a lone pair, so there's a lone pair over here. So the dipole moments cannot cancel out, since there is no dipole moment over here, so you don't have this dipole moment to cancel everything out, so there will be a resultant dipole moment. Sorry, I drew the arrows the wrong way around. This is, so D is our answer over here. In case of questions like this, you'll need to see where we have a lone pair or where we have asymmetric compounds. Like if this was CCl3H, this would be polar because the CH bond has a different dipole moment than the CCl bond, so they wouldn't cancel each other out. Now for question 6, we have which oxide of nitrogen contains 30% nitrogen by mass. So in nitrogen oxide, NO, we have the mass of nitrogen over here is 14. The total mass is 14 plus 16. And this would be the percentage by mass of nitrogen over here. This would equate to 47%. This is out. For NO2, we'll calculate again. For NO2, this would be 14 divided by 14 plus 16 into 2, which this would come out to be 30%. So this is the answer. If you want to calculate for the other ones as well, we can do that. For N2O, we'll have 14 into 2 divided by 14 into 2 plus 16. This will come out to be 64%. And if I have N2O3, so N2O3, I'll get 37%. Now for question 7, we need to calculate the mass of sodium carbonate required to make up 250 cm cube of a 0.1 mole per dm cube solution. So the volume is 250 cm cube and the concentration is 0.100 mole per dm cube. If we multiply the volume after converting into dm cube with the concentration, we'll get the number of moles of Na2CO3. So if we do that, we'll get so number of moles will be 0.100 into 250 into 10 to the power minus 3, which will be 0.025 mole. If you want to find the mass would be the molar mass of Na2CO3 multiplied by the number of moles. The molar mass of Na2CO3 was 23.0 times 2 plus 12 plus 16 times 3, and then you multiply 0.025 with the whole thing. The molar mass comes out to be 106, and the mass comes out to be 2.65 grams. So B is the answer. Now moving on to question 8, we are given a lead block of a lead cube. So this is a cube of dimensions 10 cm, 10 cm, 10 cm. We are told that it contains 3.295 into 10 to the power 25 atoms. We have to find the density. The volume of the cube would be 10 cube, so 1000 cm cube, and number or the mole number for this, or the number of moles of lead in this cube would be the number of atoms, so 3.295 times 10 to the power 25 divided by the Avogadro constant 6.02 into 10 to the power 23. So this is 54.7 mole. 54.7 mole of lead will have a mass of 54.7 times the mass number of lead, which is 207.2. This will be 11,340.9 grams, and this is 1000 cm cube. So the density, we need the density in gram per cm cube. We have the mass in gram and the volume in cm cube, so we don't have to convert anything. We'll have 11,341 by 1000, so our answer will be 11.34. So C is the answer to question 8. Now moving to question 9, we have to choose which are the correct bonding and structure for the substances listed. Copper to sulfate is an ionic compound, so this is wrong. All ionic compounds are giant, so this is correct. For graphene is a covalent compound, but it's not a simple molecular structure. It has a giant structure. Now for iodine is not metallic. It has a simple covalent structure. So this is correct, but it's not metallic. For sodium, we are told the bonding is metallic, so this is correct. And the structure is giant, so this is correct as well. So D is the answer. All metals have a giant structure, if you don't remember. Now in question 10, we are told that an excess of sodium sulfate solution is added to 50 cm cube of 0.1 mole per dm cube solution of barium chloride. We have to find the mass of barium chloride, or we have to find the mass of barium sulfate formed. So the number of moles of barium chloride used would be 0.100 times 50 into 10 to the power minus 3. So 5.0 into 10 to the power minus 3. So this is the number of moles of barium chloride. Now the mole ratio of barium chloride to barium sulfate is 1:1. So the number of moles of barium sulfate formed will be equal to 5.0 into 10 to the power minus 3 as well. So the mass of barium sulfate formed will be 5.0 into 10 to the power minus 3 times the molar mass of barium sulfate, which is 233.4. So our answer will be 1.167 grams. A is our answer. Now in 11, we are asked which compound shows the greatest degree of polarization. So the conditions of polarization are, for the cation, larger the cation, smaller the cation, greater the charge of cation, the greater its polarizing power. So that's to greater polarizing power. Now in case for the anion, larger the anion, greater the charge, will result in greater polarizability. So if the anion is larger, it's easier for the cation to distort its electron cloud. So this is the cation, this is the anion. If the anion is larger, it's easier for the cation to polarize the anion. If the cation is smaller, it's easier for the cation to polarize other anions. And if the charge is greater for both of them, the polarization increases between them. Now if we come to this, if we compare the cations at first, so we have sodium here and magnesium here. Sodium has a charge of +1, while magnesium has a charge of +2. There isn't a significant difference in their size, so magnesium will have a greater polarizing power. So sodium chloride and sodium iodide are out of our options. So our answer should be between C and D. Now if we check the anion over here, we have chloride and iodide. Both of them have the same charge of -1. However, iodide is in the period, iodine is in period 5, while chlorine is in period 3. So iodine or the iodide anion has a much larger size than the chloride anion. So iodide anion will be easier to polarize than the chloride anion. So the polarization for magnesium iodide will be greater than magnesium chloride. So D will be our answer. Now moving to question 12. We are given a sample of seaweed which contains 30 milligram of iodine per kilogram. We have to calculate the number of iodine atoms in 10 kg of this seaweed. So we have 30 milligram of iodine over here in 1 kg. So in 10 kg we'll have 30.0 into 10, so 300 milligram of iodine in this. We need to convert this into grams because our AR value over here is given in gram per mole, so we need this in grams. So if we convert this, we'll get 0.3 grams. So the number of moles of iodine in this case will be 0.3 by 126.9, and the number of atoms will be that multiplied by the Avogadro constant. If we calculate that, it will come out to be 1.42 into 10 to the power 21, or this answer over here. Now we are given that concentration of sulfur dioxide in a sample of polluted air is 0.4 parts per million. We have to convert the parts per million into percentage. Now 1 part per million means 1 in 1 million. So this is 1% means 1 in 100. So 1 ppm is 10 to the power minus 6. 1% is 10 to the power minus 2. So 1% would be 10 to the power 4 parts per million, or if you want it the other way, 1 part per million will be 1 by 10 to the power 4, so 10 to the power minus 4 parts percentage. So 0.4 ppm will be 0.4 into 10 to the power minus 4 percentage. So we'll have 4 into 10 to the power minus 3%. This will be 5. 4 into 10 to the power minus 5. So this is already out. This is 2 zeros. This is out. This is 1, 2, 3, 4. This is the correct answer. Question 14, we have to state how many structural isomers we have for C6H14. So one of them would be a straight chain alkene, a straight chain alkene like this. You don't need to draw the display. Another one of another isomer would be having one methyl group, 2, 3, 4, 5. We can either get a methyl group on the second carbon over here, or we can get a methyl group on the third carbon. So we have two structural isomers over here. One is 2-methyl pentane, the other is 3-methyl pentane. This over here is hexane. We'll also have H3C, CH2, CH2, CH3. So we have 2,3 dimethyl butane. We could also have the methyl group on the same carbon. So instead of this, we can have a carbon. We can have another methyl group over here. So that would be 2,2 dimethyl butane. So we have 1, 2, 3, 4, 5. 5 structural isomers for C6H14. Now on to question 15. We have to state which statement about polyethylene is not correct. The first statement is correct. Polyethylene is a addition polymer of ethene. So n number of ethene joined together to form polyethylene. It doesn't decolorize bromine water, so this is the answer. If you're not sure about this, you can also eliminate the other options. It is non-biodegradable, that's true. Polyethylene cannot be recycled by bacteria. It also has an empirical formula of CH2. There are twice as many hydrogen as carbon. So we are only left with option B. Now we are asked which mixture could be formed when a single molecule of C12H26 is cracked. If you have butene, pentane and propene, we'll add the number of carbon and hydrogen and see if that works out. So the number of carbon for this will be 4 for butene, 5 for pentane and 3 for propene. So the number of carbon adds up. Now for the number of hydrogen, butene is C4H8, pentane is C5H12 and propene is C3H6. So we'll have 8 plus 12 plus 6, 26. So A is the answer. If you check with the other, check the other one. So hexane, butene and ethane. For option B, we'll have 6 carbon for hexane, 4 for butene and 2 for ethane. So the carbons add up. For hydrogen, hexane is C6H14, butene is C4H8 and ethane is C2H6. So 14 plus 8 plus 6, we have 28. This doesn't add up. For this, nonane has 9 carbons. The color is not good enough. and ethene has 2. This adds up to 11, so this doesn't work out. And if we look at propene and decane, propene has 3 carbon, decane has 10 carbon, this is 13, this doesn't add up. So A is the only answer we have. In question 17, we are asked which substances are formed from the combustion of petrol in car engines. In option A, if we look, water is produced during combustion, water vapor. Carbon dioxide is also produced. Hydrogen is not produced. If we have a complete combustion, we'll have CXHYOZ plus something O2. We'll have CO2 plus H2O. So we don't have to care about the numbers, we are only looking at the products that are forming. If we have incomplete combustion, carbon monoxide and carbon can also form, but hydrogen won't form. In option B, we have water. Water does form over here. Carbon monoxide also forms if we have incomplete combustion. Hydrogen chloride, however, doesn't form in this case. In option 3, water forms, carbon dioxide also forms. You might take a while to think about this, but sulfur dioxide will also form. Usually petrol has some sulfur dissolved in it, because when we mine it from the ground, it usually has a little bit of sulfur impurity left. So when the engine burns the fuel, the sulfur goes into the atmosphere and reacts with the oxygen in there to form sulfur oxides. If you don't remember that fact, you can also look at the last question and eliminate the wrong answers. So in part D, water will form, carbon particulates will form, including CO2, CO and C itself. Hydrogen, however, won't form, so this is not the answer. B is not the answer, A is not the answer, so C must be the answer. And with that, we're done with the MCQs. Moving on to section B. Now in question number 18, we are given that compounds A, B, C and D all have the molecular formula C4H8. We are given that A, B and C each contain one double bond, but D does not. And we are given that A and B are geometric isomers of each other. Since D does not have a double bond, it must be a cyclic compound for it to have this formula. So it must be a cycloalkane. So that would be cyclobutane. D would be they want this is cyclobutane. Now we are told that A and B are geometric isomers of each other. So one of them could be, if we draw this, so we'll have the carbon double bond. We have 4 carbons, so we can have a CH3 here, a H here, H here, CH. So this would be Z butane. The high priority group is CH3 and both of them are on the same side, so this is the Z isomer. The other would be the E isomer for this, so H3C over here, CH3 over here. So the high priority groups are on opposite sides, so this would be E butene, and the possible structure for C would be this is one of the possible structures. This is methyl so this is 2 that's it for question 18a. Now moving on to part B. We have to describe the difference between the sigma bond and the pi bond. We have to include a label diagram in your answer. So at first we have to show the diagram. So a sigma bond is caused by the S shell or so this is the sigma bond over here, and for the pi bond we'll have the py shells the bond between this this is the pi bond over here. Instead of the sphere you can also draw the px orbital. This is the sigma. Now we'll describe that the sigma bond is head-on overlap of orbitals, whereas pi bond is the sideways overlap of orbits. Now we have to give two reasons why compounds A and B exist as geometric isomers. For cases like this, we have to talk about the restricted rotation. So around the double bond there is restricted rotation because of the sigma bond. If there was a pi bond only, so this and this, so this is a pi bond, sorry my bad, this is a sigma bond. If there was a sigma bond only, I could rotate this subshell about this axis, so I could rotate it like this and there would be no change. However, if there is a pi bond, so if they're overlapping like this, I cannot move this around like this or like this, because there would be a change in the orbital overlap. So if there are pi bonds involved, or double bonds or triple bonds, we have restricted rotation, and the restricted rotation causes the geometric isomers to form. So for questions like this, we'll write that there is restricted rotation about this carbon-carbon double bond. And another of the criterion, so another criterion for geometric isomers to exist is two different groups being present over here. So if we look at this carbon over here, it has a bond with CH3 and H, so they are different stuff. CH3 and H are not the same, so you need different stuff. In case of 2-methyl-proptene, if I look at this carbon, it has a bond with 2 hydrogen, so 2 identical things. So if there are if they are bonded to 2 identical groups of atom, will not have isomerism, because they are the same thing. The isomerism is caused by two different things being over here. Now moving on to question 19. We are given that this question is about 2-chloropropane. Given that 2-chloropropane has a relative molecular mass of 78.5 grams per mole, and that chlorine has two common isotopes, chlorine 35 and chlorine 37. There are 3 times more chlorine 35 than chlorine 37. The main isotope of hydrogen is hydrogen 1, and for carbon it's carbon 12. We are given a diagram that shows the mass spectrum grid. We have to draw the peaks for the molecular ions of 2-chloropropane resulting from these isotopes. So 2-chloropropane is C3, 1 2 3 4 5 6 7, so C3H7Cl. We are only dealing with one mass of hydrogen and carbon, so only one isotopes of hydrogen and carbon we'll consider in this case. But for chlorine we'll be considering two different isotopes, so we can have two different masses for that. The molecular mass might be 3 for chlorine 35. We'll have 12 into 3 plus 7 plus 35, and for chlorine 37 we'll have 12 into 3 plus 7 plus 37. This is 78, this is 80. And we are also told that there are 3 times more chlorine 35 than chlorine 37. So if there are 3/4 of all chlorine is chlorine 35 and 1/4 of it is chlorine 37. So the relative abundance will be 75% for chlorine 35 and 25% for chlorine 37. So for the relative abundance for 78 will be 75 and for 80 will be 25. $750 is over here. 1, 2, 3, 4, 5. 5 boxes is 50, so each box is 10. So this is 60, this is 70. Somewhere over here is 75. So that's our peak over here. And for the peak of 80, we'll have, this is 1, this is 10, this is 20. Somewhere over here we'll have 25. So our peak will be now in part B. We have to show the initiation step for this reaction. The initiation step will be the radicalization of chlorine. So we'll have half arrows. This forms 2 chlorine radicals. Now we have to use our answer to part B1 and state what is meant by the terms homolytic and free radical. The definition of homolytic is each of the chlorine getting 1 electron when the bond breaks. So when there is an electron pair over here, one of the electron will go to this chlorine, one of it will go to this chlorine. That's the definition of homolytic. If heterolytic means that if there is a bond over here, so there's an electron pair over here. After the bond breaks, this chlorine takes away both of it, while this gets not. This is heterolytic. This is homolytic. The definition would be each atom gets and free radicals are species that have an unpaired electron, like this chlorine over here. Its outer shell will be like this. There's an unpaired electron over here, so this is a free radical. In question B3, we have to suggest why this method has limited use in the synthesis of organic compounds. And this could be due to the formation of multiple products that we don't need. So if we want to get one organic compound, using this method we'll get some of that compound, and we'll also get other compounds forming, because there are a lot of substitution reactions going on. Now in part C, we are told that 2-chloropropane can also be produced from the reaction of propene with hydrogen chloride. Propene is CH3. This is propene and this is hydrogen chloride. So for this we'll have HCl over here. The hydrogen is electropositive while the chlorine is electronegative. The electron rich double bond will break, giving hydrogen its electrons, and the hydrogen, this bond will break, giving chlorine the electrons. Then we'll have H the hydrogen will join the carbon which has the most hydrogens already. So this carbon over here, this carbon already had 2 hydrogen while this carbon had 1. So this was 2, this was 1. The hydrogen will for the major product will join the carbon that has more hydrogens attached to it beforehand, and this will form a carbocation. The chlorine minus that we have from this bond breaking will be here, and it will attack the carbocation over here with its lone pair of electrons, and we'll get H3C, CCH3. So that's the mechanism for this. Also, if we move back to this question, the suggest one, the more products forming will be due to we have the chlorine over here. So the chlorine free radical will join any of the carbons. The chlorine radical can attack any of the carbons over here. If it was a longer chain, this would the problem would be even greater. So if I had a chain like this, if I want the chlorine to join carbon number 2, we might have a problem because we'll also have chlorine joining this carbon over here and this carbon over here. Sorry, that's symmetric. So we'll also have chlorine joining this carbon over here, which we don't want. We don't want the chlorine joining over here. This is an unwanted product. We only want this. If the carbon chain is even longer than this, the problem will be even greater than that. So for synthesis of organic compounds, this method has only limited uses because of this problem. Okay. Now moving on to question 19C2. We have to explain why only a small amount of 1-chloropropane is produced in this reaction. So what we got over here is 2-chloropropane. In this reaction, the minor product will be this over here. So for the production of the minor compound, CH3H. In this case over here, we'll have the hydrogen joining here, and this being our carbocation. So we'll have H2C Cl CH2CH3. So this over here is 1 chloro propane. This would be the minor product, because we know that if we go here, no. Uh, 1 degree carbocations are the least stable, while tertiary carbocations are the most stable. When 1 chloropropane is being formed, we have this carbocation over here, which is a 1 degree carbocation. So this is less stable. In this case, however, when we are forming 2 chloropropane, we have a 2 degree carbocation or secondary carbocation, which is more stable than a primary carbocation. So this over here is more stable than this over here. So we have to answer our question based on the stability of carbocations. So this is how we'd answer this question. We talk about how 1 chloropropane is formed via primary carbocation. We cannot write that 1 chloropropane is a carbocation itself. We'll lose our marks for that, because this is not a carbocation. This intermediary step is. Same case for 2 chloropropane. We are not telling that 2 chloropropane itself is a secondary carbocation. We are telling that it's formed through a secondary carbocation. Now moving to question 20. We are given that magnesium contains 3 isotopes and has a relative atomic mass of 24.32. We have the abundances for 2 of them. We have to calculate the relative abundance and the mass number of the third isotopes. Total abundance would be 100%. So 78.99 plus 10.00 plus the relative abundance of the third particle, I'm assuming a mass number of n and the abundance of X for the third one. So this plus X would be equal to 100. So the total percentage would be 100. So if we add up the abundances of each of the individual isotope, we'll get 100. So the abundance for that would be 11.01%. Now we know that the atomic mass is 24.32. So 24.32 is equal to the relative. In this we'll have the relative abundance times mass number of each of them times the total abundance divided by the total abundance. So for this case we'll have 24, mass number is 24 and its abundance is 78.99. When mass number is 25, its relative abundance is 10.00, and when the mass number is m, what we want to find, the relative abundance is 11.01 divided by 100, we get 24.32. Now we'll multiply 100 on both sides. So this times 100, this times 100, we'll get rid of this. So we'll have 2432 equals to 24 into 78.99 is 1895.76 plus 250 plus if we calculate this will 26. So m is 26. Now we have to state one similarity and one difference. The similarity is the number of protons and the difference is the number of neutrons. So they have the same number of protons. So basically the similarity of difference between any kind of isotopes. Now we have to state which of these isotopes would be deflected most in a mass spectrometer. In a mass spectrometer, the lower the m by z ratio, so the mass by charge, lower the ratio, the greater the deflection. In this case, the charge would be the same for H plus 1. And the mass of magnesium 24 is the lowest. So the deflection for magnesium 24 would be the highest. So magnesium 24 would be deflected the most. We're justifying our answer. So we'll write magnesium 24 would be deflected the most because it has the lowest m by z ratio. Now moving to part B, we have to draw dot and cross diagram to show the bonding in magnesium oxide MgO. So this would be an ionic compound. So we'll draw the outer shell of magnesium. The magnesium will lose its outermost shell, so 2 of its electron, and it would give it to oxygen. Let me draw it in red. And this would have a charge of +2. And now we'll have the oxygen over here. The outer shell of oxygen had 2 lone pairs, and it received 2 electrons from magnesium to make its outer shell full. So this would be the diagram, and it would have a charge of -2. Now we are given that the melting temperatures of magnesium oxide and magnesium sulfate are 2852 and 1124 degrees Celsius respectively. We have to explain why the melting temperature of magnesium oxide is significantly higher than that of magnesium sulfate. The anion is the cation is the same for both magnesium. The difference is caused by the difference between the oxide, so O2 minus, and the SO4 minus. So the difference is caused by the difference between the anions. The difference between them is their size. So on the oxide anion is much smaller than the sulfate anion. So there are stronger electrostatic force of attraction between the Mg2 plus and the O2 minus, and that causes the higher melting temperature. So we'll write now in part C, we are given this table of the electrical conductivity of magnesium and magnesium oxide in solid and liquid form. Magnesium has a high electrical conductivity in both solid and liquid form, while magnesium oxide has a low conductivity as a solid and high as a liquid. We have to explain the similarities and differences in the electrical conductivity of the two substances. Now, magnesium is a metal, so it has delocalized electrons which are free to move, and the delocalized electrons are there when it's solid and when it's liquid in both phases. So magnesium has both when it's solid and liquid. Now, in magnesium oxide, In solid form, there are no delocalized electrons because the magnesium has a full outer shell, the oxygen has a full outer shell. They won't give away any electrons. However, if they are in liquid form, the ions itself, so the magnesium 2 plus and O2 minus ions themselves are able to flow through the liquid and move and conduct the charge. So we'll write magnesium oxide is the ions in magnesium oxide are free to move only when it's liquid. Moving to part D, we are told that magnesium sulfate can be made by reacting magnesium with dilute sulfuric acid. We have to write an equation for the reaction that occurs, including state symbols. So magnesium plus dilute sulfuric acid, so H2SO4, and this results in the formation of magnesium sulfate, MgSO4. We'll also form a hydrogen gas because this is a reaction of metal plus acid, so we'll get salt plus hydrogen. You can remember this by the acronym, this acronym. So metal, acid, salt, hydrogen. Magnesium is a solid, dilute sulfuric acid would be aqueous, magnesium sulfate would be aqueous, it's soluble in water, and the hydrogen gas. Now we have to give two observations of this reaction. We see that here we have a solid, in this side we don't, so we can write that the solid disappears. This is one of the observations. Another observation would be the bubbling or fizzing due to the hydrogen gas being formed in an aqueous solution. So the reaction is taking place inside a beaker. This is H2SO4 aqueous, and you put the magnesium thing over here, whatever you want to test. You can react a magnesium foil or a magnesium ball. So this is the magnesium solid we will be reacting. If hydrogen is produced over here, there will be trapped gas in a liquid, and this would cause bubbling or fizzing. So we can write fizzing of H2 gas. I don't even have to write it's due to H2, so this part over here is optional. Now in part E, we are told that hydrated crystals of magnesium sulfate, MgSO4 can be made by reacting magnesium with sulfuric acid. We're given that in an experiment, 30 cubic centimeters of 0.5 mole per dm cube sulfuric acid, that magnesium was added to this concentration of sulfuric acid. In part 1, we have to calculate the number of moles of sulfuric acid used in this. So the number of moles would be the concentration times the volume in dm cube. So we have to convert the 30 cm cube into dm cube by multiplying it with 10 to the power minus 3. we'll get 0.5 into 30 into 10 to the power minus 3, which comes out to be 0.015 moles. Now we have to calculate the mass of magnesium needed to react with the sulfuric acid. So the mass would be the number of moles times the molar mass of the atomic mass of magnesium. This would be 0.015 times 24.3. We'll multiply 0.015 because the mole ratio of magnesium to sulfuric acid is 1:1. We found it in the previous part. This will come out to be 0.3645 grams. We'll give a reason why slightly more than this mass was used. We do this so that the sulfuric acid is the limiting agent in this case. So we'll use excess magnesium to ensure that all of the sulfuric acid is used up. Now in part 4, we have to state how the magnesium sulfate solution could be separated from the mixture produced in this experiment. So this was the reaction over here. In our case, we have magnesium in excess. So after the reaction is complete, the reaction mixture will have some magnesium solid left, the magnesium sulfate solution. The hydrogen gas will leave the solution, and H2SO4 is limiting. So we have to separate the magnesium sulfate from the magnesium solid. So as we want to separate solids from a liquid, we can just use filtration. Now in part 5, we are given that after they were allowed to crystallize, the mass of hydrated crystal was 2.78 gram. So the actual yield over here is 2.78 grams. We can find the theoretical yield. The number of moles was 0.015 and the molar mass for hydrated magnesium sulfate is 246.4. So the theoretical yield would be 3.696 grams. So the percentage yield would be 2.78 by 3.9696 times 100. So we have a yield of 75%. Now moving to question 21, we are told that boric acid contains 17.48% mass of boron and 77.67 of oxygen, and the rest of it is hydrogen. So boric acid is, we have to show that its molecular formula is H3BO3. So if we make our table, we have percentage by mass. So hydrogen is boron is 17.48, oxygen is 77.67, hydrogen would be 100, the total percentage minus the rest of it, so minus 1.48. So we'll be left with 4.85. The number of moles or ratio of moles would be 4.85 by 1, 17.48 by 10.8, and 77.67 by 16. We'll have 4.85, 1.6185, and 4.854. We divide the values by the smallest one, so 1.1, 1.6185. We get 1, 3, 3. Now we know the empirical formula is H3BO3. Now we have to show that the molecular formula is H3BO3 as well. We are given that the molar mass of boric acid is 61.8 gram. So we'll find the mass for the empirical formula, which would be 3 plus 10.8 plus 16 into 3. This is 61.8 gram per mole. As this is equal to the molar mass of boric acid, the molecular formula would be equal to the empirical formula. Therefore, molecular formula is H3BO3. Now we are given that the formula for boric acid can also be written as BOH3. We have to show a dot and cross diagram for this molecule. So we have the boron. Boron has 3 electrons in its outer shell. It will share it with the OH, so 3 OH over here. I'll consider the oxygen having this. Oxygen has 7 electrons in its outer shell, so 1, 2, 3, 4, 5, 6, 7. Same here. Now one of this for OH is for the hydrogen. This is hydrogen's electron. These are oxygen's electron, and this is boron's electron. We have to suggest a value for the OBO bond angle, justifying our answer. We have 3 bonds over here, so 3 single bonds. So if we remember our table or the bond angle chart, for 3 bonds with no lone pairs, we have a bond angle of 120 degree, and they have a trigonal planar shape. So we'll We also have to justify our answer, so we'll tell that as there are three we also have to write that they will adopt a position of minimum repulsion. For any questions regarding the explanation of bond angles, we have to mention this point. Now in question 22, we are given that the density of unknown gas is 0.656 at 20 degrees Celsius and 101,000 pascals. We have to find the molar mass of the unknown gas. Using PV equals to nRT, we'll find the number of moles N, and then we have to use the density to convert this number of moles into the molar mass in gram per mole. So for N, density is in gram per dm cube and the molar mass would be in gram per mole. So we have to eliminate this gram per dm cube. So we could take the number of moles in 1 dm cube of the unknown gas. So we can change this into mole per dm cube as well. So if we divide the density by the number of moles, we'll get gram per dm cube by mole per dm cube. This will cancel out, we'll get the answer in gram per mole. So to use PV and RT, however, we need the volume in meter cube. So we'll convert 1 dm cube to meter cube. So 1 dm cube is 10 to the power minus 3 meter cube. The pressure is 101,000. The volume is 10 to the power minus 3 equals to N into 8.31 times the temperature in Kelvin, so 20 plus 273. From here we'll get the value of N, which is 101 by 8.31 into 293. So this was 0.04148 gram per mole. And the density is 0.656. If we divide it 0.0418, we get 15.8 gram per mole. This is the molar mass of the gas. Now we're told that the unknown gas is a hydrocarbon, and we have to give the name or formula for the unknown gas. So we need a hydrocarbon with a molar mass of around 16. If we check some Alkanes, if we try methane, for example, we'll have 12 plus 4. Yeah, this is 16. So this might be methane. So this is the answer, and that's it for this paper.